This is our final session on state machines. In this session, we're going to learn how to implement state machines. In other words, that I believe from the previous sessions, we should all agree that we know what state machines are and how to create a state machine. The state transition table or the state diagram, depending on how you want to do it. But then we need to figure out how to get this on a robot. If we're going to put it on a robot, this is all an issue of software. And for FTC, the software we're going to be using is Java, and we're going to be writing then a set of methods and Java statements that will implement each state machine in our robot. As indicated down here, a state machine is basically just a method. In this case, the method is arm, and with a series of statements that would each statement would be determining if this is the current state and performing that function. So as if it goes through these if statements, then you'll pick the right functionality to execute when depending on the state. So there is a private variable up here, which is unique to ARM, and it's called state. Generally, some initialization process will assign state equal to 0, okay, at the beginning, and then afterwards we would execute this statement. Now, the trick here, when we call ARM, as it moves down through states, for example, let's say our current state now is 1, it will stop here and it will perform this function. Now, what is that function? Well, we've seen in state machines, we were going to look for inputs. And these could be driver inputs, or they could be things like encoder reading or button pushes or whatever. We will produce outputs to make the robot do what we want to do. Simply, typically that's setting motors, these kinds of things. And then we will go through and determine next state. Now, when we do next state, it's important to understand that the next state many times is the current state, right? So there will be some function or some determination in when to advance to the next state. And the next state is not always state number 2. The next state could be back to state 0, or the next state could be state 3. So in this example, so don't lose track of the fact that we're writing all of this to do what that statement, to execute that state machine or perform that state machine. So in this case, some of you may be a little bit concerned that if we're in state 1, and then we find out that when we perform the function of that state, the next state we want to execute would be 3. That when we leave this if statement, we'll basically trip through here. It's not 2, so we don't execute functionality state 2, but it's 3. We will immediately execute the functionality state 3. Now, that generally is not an issue. Many state machines I write, you can execute multiple states as long as they're in order, okay, if necessary. If this is a problem for you, then when we execute the state, what we do, or when we want to do a next state, we'll just simply use an interim variable, let's say called new state, and we would assign new state equal to 2 or 3, and then we would jump down here, and we would, before we go here, we would then at the very end update the state. So by doing that, we don't execute multiple states in one pass. Now, when I talk about one pass, it's important here to understand that every time the ARM is called, it's just going to execute one of these states, with the possibility we talked about before of executing maybe subsequent state. But and then after it executes the functionality of that state, it returns, ARM returns. And so we can basically so then we'd have to call ARM again, and ARM again, and ARM again, until you get Armageddon. That's a joke, but don't worry about it. And so we will have to see how where these state machine methods are actually in the robot. And that brings us to the next slide. Okay, actually, no, let's do this one first. Let's look at an example of how we can map a state transition diagram, okay, or a state table into code, okay, and this is all pseudocode again. Don't write this and expect it to run. Okay, so we're going to start here. This is, by the way, the first two states of our ARM state machine, okay, that we developed earlier. So you may want to review that if you don't remember it. And so the first thing we do is we start with state 0. Okay, that was our initial state. So state 0, then when we call ARM, if we're in state 0, we're going to execute this set of code. So what is that set of code? The first thing is we take care of the output, which is equal to here. So we turn the motor off. Okay, and then we determine what the next state is when that's all of this stuff along here. So what is the next state? If the button is pressed, we will go to state 1. So you can read it right here. If button is pressed, we go to state 1. If the button is not pressed, we just stay in state 0. So we don't change the state variable on this one. So you can see there is a nice mapping between this set of stuff and that set of stuff. Now let's go on to the next state. That would be state 1. And in state 1, we will, right over here in state 1, okay, we can see where state 1 is, the function of state 1 is being executed. It's right in this line of code. So what do? The first thing is we take care of the output. So it says set it to power, positive power, and in this case, in our design, we would set it equal to positive 70% power. Okay, that would be the 0.7. Okay, so we basically took care of that with this line. Now we need to look at the inputs, and the inputs are the switch state, pressed or unpressed, and then the encoder state. And this is it greater than or less than that upper limit, 562. Okay, so we look at that. Now, when we're doing that, let's take a look at the simplest transition. The simplest transition right now is to just stay in state 1. Okay, so to stay in state 1, we just don't do anything. Okay, so let's say the next one is to go to state 2. Go to state 2, there's only one column of this, or row of this table that goes to state 2, and that says if the button is pressed and we're greater than 562. And we can see that is right here. So if the button is pressed and we're greater than 562, then we go to state 2. And so we would have that, okay? The state 3 is another transition, and state 3 is actually here and here. So let's look at what causes us to go to state 3. The button being not pressed, the button being not pressed, or the encoder is less than this, or the encoder is greater than. So if it's less than or greater than, does the encoder change whether we go into state 3? No. So what happens is we're only interested in the transition to state 3 is the button being pressed or not. So we say if the button is not pressed, then we go to state 3, and then we leave. So I hope you see that there is, in a somewhat more complicated state transition, there is still a very easy to map set of lines of Java that would basically execute, that fully executes this particular state. Now, how do we complete the state machine for the ARM? Well, we'd have to do the same thing to states 3 and state 2. But I think you'll find, and I invite you to do that right now, is actually to look at the state machine for states 2 and state 3 in the in the ARM and see if you can write the code that would execute those. And I think you'll find that the code is virtually identical to what we did here. I think state 2 looks a lot like state 1 transition, and state 3 looks a lot like state 0. And so you could just write the entire state machine this way. So I trust that from this you can see there's a very straightforward mapping from state machines to code. Now, we talked about in a typical robot, we'll have many state machines. We'll always have one state machine, which is kind of a silly state machine, which is the driver state machine. It looks at the state of, typically the state of the stick on one of the game pads, and then determines motor power. But we could have all kinds of state machines. So here we have a suggestion that we have 5 state machines. This would be one state machine. 2, we got an ARM on this robot, so we might as well use the ARM state machine. We have 3, 4, and 5. So what we do is we simply just take the methods and we call the methods one after the other. So in this case, we would call 5 methods in this, in the main loop of the robot. After we finish with this state machine, we go back up and we call the state machines again. So it goes around and around. Now, for reasons that well, we might as well explain it now. We can't have this just call the state machines one after the other very, very quickly. Because in a typical robot, that means that this thing will execute thousands of times a second, which is, number one, you don't need to do that. And number two, it can actually cause a problem with the robot's operating system, okay, the stuff that's given to you by FIRST. So in a way, we need to slow this thing down so we don't cause a problem with the operating system. And in a typical robot, what we do is we slow it down so that each of these states is called one after the other in about 20 millisecond period. So every 20 milliseconds, these state machines, each state machine will run one after the other. And 20 milliseconds is 50 times per second. And 50 times per second is plenty fast to control a robot. Robots don't move that fast. Drivers don't flip buttons that fast or change game pads that fast or sticks that fast. So we find that this is a good speed that is a good balance between the needs of the robot and the needs of the robotic operating systems to not run too fast. Now, if it's going to execute every 20 milliseconds, the main thing to do is that each one of these state machines, the methods executing a state machine, has to quickly return to the main loop. Because if one of these state machines takes, let's say, 30 milliseconds to execute, then what happens? These other state machines won't be executing during that time. And we can actually have a situation where for example, if the driver state machine doesn't execute or the drive state machine doesn't execute, then what happens is the driver can zero the gamepad, but the robot will still be running and run right into the wall. So for that reason, we want to make sure that each one of these state machines is running very, very quickly and returns into this loop. Okay, so that's very important. Now, as pointed down here, is that I already said that you have to control the timing of this loop. So you have to control the timing. Typically what happens down here, there's a little piece of code that does a wait. And it does a computed wait. So what happens is that you wait a period of time so that this loop will run in 20 milliseconds. Now you say, well, that's easy. I'll just put 20 milliseconds here. But if you put 20 milliseconds here, what happens is this loop will actually run more slowly than it should because you're not accounting for the time it takes to execute each one of these 5 state machines. So you have to compute this. And also you find that as you go down this list, every time you run this, depending on which state, you may find that it takes a little bit longer. One state machine needs to takes a little bit longer, or it runs a little bit faster. So you need to do a dynamic calculation on this to make this work. Okay, this is just a warning, okay, and it's going online and searching for Java state machines. And if you go online and search for Java state machine methods, you'll get a ton of them, okay? And some of them are really neatly implemented. It's not these silly if statements. But I strongly recommend not doing that, because in the past, students who have done that have ended up in a big mess because they don't understand how the state machine is actually running. The best thing to do is to keep it simple. And as one of my teachers used to say, learn to crawl before you walk, learn to walk before you run. And I think that this is really important here. So let's just do the if statements and write your own state machines, and so you understand how it works. We can go off and do something more complicated later. Okay, so let's look at some other things on software considerations. Well, one of the things that needs to happen in a state machine is you have to initialize it. You have to make sure the state machine starts off in its initial state, and maybe any private variables within the state machine are set up correctly. So we have to always begin initialization state. Okay, so you say, well, when we just power it on, everything will be initialized and that's fine. But you know something? We've found out that it's a lot better to explicitly initialize. So every time you start, let's say, in teleop or start in autonomous, you explicitly initialize all of the states. Okay. Now, obviously, you need to also do initialize during power on. Make sure all the states are in their proper initial state, but you should also do it at resets or just basically starting teleop again. Okay, this requires that we need to be a little bit more sophisticated. When we do a state machine method, we need to pass a parameter into it. Okay, now mode could be an enum, or it could be an init, or it can be anything you want. Okay, but what typically for initialization, what we want to do is we want to call the state machines with the mode indicating that the state machine doesn't run as a state machine, it just initializes itself. Okay, so this is kind of an overhead, or it's sometimes called housekeeping on the state machine. Then once all the state machines are called with this mode being in the init parameter, and by the way, init could be a 0 or a normal could be a 1. It doesn't need to be enum. You might as well just enum it so you can read it. And then when the code actually starts running, then we call each one of these state machines in that 20 millisecond loop with mode being normal. So that means the state machines will run in their normal way, and that causes the robot to work. So this is a little bit complex. It raises the complexity because you have to pass a mode into the state machine. And the init and normal are generally what's done, but there may be other things you need to do to basically kind of configure or manage the state machine. The other thing you need to do, possibly in software considerations, is you need to talk about state machine error handling. So every time we call the state machine, we just assume it runs fine. But sometimes state machines will find there's a problem. There's an error that it can't deal with. Okay? And so we would like to know how the state machine is running. So the trick is that you return a value from the state machine that the main program can look at. And what would be that value? For example, you could have a value that's called busy. okay, says that the arm is busy, it's moving. You could have another return that says that the arm is idle, which means it's just in its default or start position and it's ready to move. Or you can have another situation where you say you found an error. Okay, so returning errors turn out to be really, really important, and also probably the most difficult part of a lot of robotics. Now, let's talk about what kind of errors we can get in an arm. So, for example, we could find that the arm is stuck. And what do we mean stuck? Well, the arm is supposed to be moving, but it's not moving. And so how would we determine that? Well, the state machine is reading the encoder, isn't it? So the state machine could say, we have the motor energized, but the encoder is not moving. Okay, and so we can assume that the arm is stuck. What would cause the arm to stick? Well, you could have a hardware failure. Okay, that bent or somehow destroyed or damaged. The other thing you could do is you could be trying to raise the arm while you're under something or another robot's on top of it. So if the state machine determines that the arm is stuck, it simply returns this error message that says arm is stuck. Okay, and then the other ones you could have an arm sluggish. An arm is sluggish is the encoders are changing, but they're changing way too slowly. There's something wrong with the way the arm is moving. You could also have a fatal error. A fatal error would be one that the state machine determines that there's something fundamentally wrong with the mechanism. It's broken and it should not be used. So as you think about your writing your state machine, you should also think about the kinds of errors or the possibilities that the state machine what the state machine may feel or exhibit as it runs, and then make sure that you pass these things by. So how do you pass it back? Okay, so we had, let's say, arm, and we talked about you could pass in a mode, like for example init or normal, and over here you could return status. Okay, and so this would be arm status, so you probably want to put a arm in front of it. And so this initializes the state machine or has it run normal. This is something that the main program, that loop, that 20 millisecond loop, can look at and determine what to do with the robot. So anyhow, I believe that is, no, we got some more. No, it's right. I forgot I had that already. So let's take a look at this. So this is what it would look like. Arm status is equal to arm mode, where you would do the things that we talked about. So this would be the general form of the method that would invoke a certain state machine. So think about this and see how this would apply as you're programming your state machines. Now I think that's the end of the discussion, and it is. So we have gone through state machines, and we've gone through the design, the theory, and the design through a series of examples, and we've talked about software considerations. You should sit down and try to write a little bit of Java to see if you can actually put together a method that would execute the state machines that we've actually done. Again, this is pseudocode that I'm giving you, so don't simply copy what I've done. Okay, with that, we're done with state machines, and then we can go on to some of the other considerations as we think about programming robots. That's the end of this discussion.